It's time for some maths. All right, today, what do we have for you? I have decided to delve into the depths of the step questions, the dreaded step 3. I found this really sweet differential equation question. Brings a whole lot of stuff. Let's see what we can do with it. We have a function yn, so that already tells me we're looking at a sequence of functions, a family of functions that are going to depend on n, and they each satisfy this differential equation. Don't be scared, but what we do have, it's second order, but we are used to having constant coefficients even at the majority of the further maths syllabus. We've got x squareds knocking about. Okay, let's not panic yet. We're given these conditions. We're told that yn of 1 is 1, okay, but then we've got this weird condition here. Yn of x is minus 1 to the n, yn of minus x. So it's given me a relationship between the function yn at x and at minus x. And really what's going to happen is as n changes between odd and even, if n is even, yn of x is equal to yn of minus x, that is what we call an even function. Okay, the values at x and minus x are the same, think the cosine curve. All right? Whereas if n is odd, yn of x is minus yn of minus x, so y of x is negative y of minus x, think an x cubed curve, all right? Or think a sine curve, all right? Sketch them, you'll see what happens. All right, we'll see how that works. Now, luckily, they are helping me out. They're telling me we're going to make this substitution. In fact, we don't want to work in x's. In x's, this looks horrible. It looks absolutely horrible. So instead, we're going to change this variable theta using the change of variable x equals cos theta. And if we do that, something nice should happen. All right, fine. I trust in the maths gods. They've told me this is where I want to go. Let's give it a go. And then we'll deal with the rest of it later. Let's find yn as a function of theta. We can do that. And then another thing to deduce. But let's start with part 1, part 2, part 3. I wonder if this board is big enough for all of us here, maths. Okay, x is cos theta. Whenever you want to make a change of variable like this, really what you want to do is go from dy dx to dy d theta. So let's start at dy dx. Get this the correct way around. Well, we're just going to use the chain rule. That is dy d theta times d theta by dx. The joys of being tall is I've got access to all of this part of the board. Right. Now, we probably want that. The nicest way to do it is still just dx d theta is minus sine theta. That's what we're going to use an awful lot of. And that tells me that dy by dx is, tell you what, let's go sideways. We are not going to have enough room otherwise. So that is dy d theta times minus 1 over sine theta. So I'm set to replace that in for that. Nice, okay, fine. Not sure how it helps me yet, but we'll get there. And now, d2y dx squared, we are going to do d by d theta of dy dx, which was this, if we remember, times by d theta dx. So I'm doing the exact same chain rule. Basically, if I want to differentiate dx, I differentiate d theta and times by d theta dx. So to get from dy dx to d2y dx squared, I need to differentiate this. So I'll differentiate this with respect to theta and then times d theta by dx. Got it? I hope so. I got a little muddle there in the middle. All right, so now we've got a product rule. So what does this product rule tell me? Differentiate that to get d2y d theta squared. Keep the minus 1 over sine theta. Keep the dy d theta. And differentiate minus 1 over sine theta. What's that? The sine theta to minus 1. So I'll get 1 over sine squared theta, and then differentiate the sine to get cos theta. and all of that times minus 1 over sine theta. Getting a little bit tight in space here. Hopefully you can see, zoom in and zoom. There we go. Okay, let's tidy this up just a smidge. What do I end up with? I end up with 1 over sine squared theta d2y d theta squared, and minus cos theta over sine cubed theta dy d theta. Okay, fine. We're going to have to sub that back into here. So what does that give me? So let's sub all of that back into my equation. Let's call this equation 1. All right, so let's sub all of that back into equation 1. We end up with 1 minus x squared. You might start seeing where we're going with this. 1 minus cos squared theta. Is this too small? Is the writing too small? Don't know. d2y d theta squared. Nope. Nope, 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 nope. Let's write this differently. Let's write this differently. d2y d theta squared minus cos theta over sine cubed theta dy d theta minus cos theta times dy d theta, which is there. So minus becomes a plus sine theta dy d theta plus n squared yn. Oh, I should probably make a little effort at putting these n's in here. They may disappear as we go through. The more astute amongst you will, of course, realize that 1 minus cos squared is sine squared. And what's going to happen? I get sine squared divided by sine squared, which will give me d2yn d theta squared. Now, what do I get? Tell you what, I think we're going to have to rub out the board anyway. So minus cos theta over sine theta dyn d theta plus cos theta over sine theta dyn d theta plus n squared yn equals 0. And what's going to happen? Kush ponk, and we're left with the result that we wanted. Boom. Lovely. Not even mildly straight, but that's okay. Just tilt your head. Right, hence, let's solve this. Okay, I reckon I've got space to solve this here. Do you know what? Our labeling is getting confusing. And I wouldn't want to be confusing, would I? Let's have that as a B, and let's have that as a C. So let's go to B. I reckon I've got space for B here. He says, now first things first, obtain yn as a function of theta. Well, you will recognize here, or here, or here, or here, you will recognize SHM. That is simple harmonic motion. Really just a general result. I can solve this very easily to get A cos n theta, and let's call it an plus bn sine n theta. Why an and bn? Well, a and b are going to depend on the value of n, I reckon. So let's just give ourselves that option. Now, we know conditions based on the value of x. So little aside here, what do we need? Let's do that over here. Yn, when x is 1, yn is 1. Well, that's in terms of x, so I do need that in terms of theta. If x is 1, that tells me that theta is 0, because cos of 0 is 1. Trigonometry. So let's plug that in. I know that 1 is an cos of 0, which is 1, bn times sine of 0, which is 0, So that gives me already the result. AN has to be 1. Smashing. Now BN is a little bit more tricky. We need to figure that one out. Well, what we do know is this, is that cos of theta is minus cos of pi minus theta. Now, why does that interest me? Well, because I need to link, this condition is in terms of x and minus x, x and minus x. So the value, if theta gives me the value of x, what value of theta will give me minus x? It will be pi minus theta, right? That's the idea we're going for here. Because we are changing variable, I need to know what happens to my variable within this condition. So if cos theta is x, cos of pi minus theta is minus x. All right? Got it? Got it. So I know that cos of n theta plus bn sine, let's put some brackets around this, it's going to be helpful in a second, n theta is equal to minus 1 to the n of cos of n plus 1 theta plus bn sine of n plus 1 theta. Have we disappeared off the screen yet? No. All right. So what we need to do is we need to compare, not n plus 1 theta, what am I on about? What am I on? Honestly. Let's make that a little bit nicer. Okay. Cos of n times pi minus theta and n times pi minus theta. Yeah, that's better. That's better. Okay? All right, fine. So all I've done is I've used this with this. Now, I do need to know something about what's going on in here. What is cos of n pi minus theta? Well, cos of, let's go n pi, let's expand it out, n theta is equal to, I'm very much on a slant down here, but there we go. That is cos of n theta. Now, cos of n theta is minus 1 to the n. Cos n theta plus sine of n theta, and sine of n theta is 0, so we're going to get rid of that. And then sine of n pi minus n theta will be sine of n pi cos of n theta, well that's 0, minus cos of n pi, which is minus 1 to the n, sine of n theta. All right, so let's just bring that down to here. Cos n theta plus bn sine of n theta is equal to, now, we've got a minus 1 to the n times minus 1 to the n cos n theta. Well, no matter what, minus 1 to the n times minus 1 to the n is always 1, right? It's essentially, it alternates between plus or minus 1, and you square it. So that just comes out as cos of n theta, so isn't that nice? And then I need to multiply that by that, because we're multiplying out, right, there to there. Minus 1 to the n times minus 1 to the n. Well, the same reasoning is minus 1 to the n times minus 1 to the n is just 1. So I'm left with that minus, so I'm left with minus bn sine of n theta. Well, what does that tell me? The cos n thetas are irrelevant. And we're left with the fact that bn sine n theta is minus bn sine n theta. Well, the only way that can work if it's bn is identically 0. Look at that, there's a lot of working there. And there we have it. I'm going to have to scoot all of that up there because you've still got a part C to go. But I think that's just a really cutesy way of dealing with a second order differential equation. We make a cool change of variable, results in a really simple SHM equation over here that we can solve really quickly. And this condition here is funky as all hell once you plug it in and sort it out, and stuff cancels out and you're left with, it sorts you out with your AN and BN. It's absolutely amazing. Right. So what does that give me overall as a result before we go into part C? Well, that's told me that yn is cos of n theta. We got our an was 1, our bn was 0. Whiponk. I mean, if you really wanted to, you could write that in terms of x. Don't. It's horrible. You'd have a cos of an arc cos. Why do that to yourself? Honestly. Honestly. Right. We're going to deduce this stuff here. So first thing, we need to show that y0 is 0. Well, n is 0. y0 is cos of 0 is 1. Isn't that nice? And for n is 1, is that the one I want to show? Oh no, what I wanted to show earlier on is y1 equals x. There we go, I wrote it out wrong. y1 is in fact x. y1 is cos of theta, put in n is 1, which is x. So far, so good. Now we want to show this. Okay, a recurrence relation. Now it's a show that, it's not prove that. We want to deduce that. So we're not going to be able to use proof by induction. It does look ripe for a bit of proof by induction. No, not allowed. So we're going to have to go from scratch. So let's have a little look, see at what these things are. Well, yn plus 1 is cos of n plus 1 theta. Can you see where my brain short-circuited earlier? But that is just what? Well, really, we want it in terms of yn. So let's just see what happens. That is cos n theta cos theta minus sine n theta. Let's just put some brackets around. I just feel bad for the sine, really, because otherwise it's synonym in the theta, and I just don't think it should. So there you go. That's the way my brain works. And let's have a little look, see at what that means for yn minus 1. That is cos of n minus 1 theta. And in fact, multiple angle formula. And you might be able to see where this is going now. You might be able to see where this is going. Because, oh look, I know cos n theta in terms of x. Yay! Right, that's fine. However, what? We don't have anything with the signs, but a minus and a plus. So if I add these two things together, what do I end up with? We end up with yn plus 1 plus yn minus 1 is equal to 2 cos n theta cos theta. However, yn plus 1 plus yn minus 1, cos of n theta is yn, and cos theta is x, which gives me this recurrence relation. Let's write it in the way they want us to. The mystical they. Kibosh! And there we go. Oddly, for a step question, that last bit was the nicest bit. Normally, it gets worse and worse and worse. Et voila! What did you think of that? Apart from the teeny tiny writing and it's all happening down there. Not too scary, right? Step, very accessible. Let me know what you think in the comments. Where else might you want me to go? Are we enjoying the step questions? Just pop it in there. Thoughts, hopes, dreams, prayers. Just whack it all in. I'm Nick. This was Nick Does Maths. Don't forget to subscribe and I'll catch you next time.